All right, so in part one, we plotted the location of 17 different seismic stations using the geocentric angles determined in the records section of the 2010 Haiti earthquake. We used this model to determine the linear distance to the Earth of each station from the epicenter of the earthquake. Remember, we are testing a hypothesis. We want to know if the Earth is made up of solid rock. And since we can't dig all the way through, we are relying on seismic data to give us evidence to support this claim. So we want to be able to relate our model back to the actual Earth. To do that, we need to determine the scale of our model. We know that the average radius of the Earth is 6,371 kilometers. If we measure the radius of our Earth on our model, we find it to be somewhere around 19.7 centimeters. So this is just a proportion. Every 20 centimeters or so on our model represents 6,371 kilometers on the real Earth. This means then that 1 centimeter on our model will represent 320 kilometers on the real Earth. So for every centimeter that we measure on our model, in real life, that's 320 kilometers. Using this scale, we can determine the linear distance through the Earth of each seismic station from the epicenter by measuring the line on our model in centimeters and then multiplying that by 320 kilometers. We want to do this for each line and then record this in the distance seismic wave travels in Earth on your Google Sheet. Now we know that the speed of a seismic wave traveling through rock is 11 kilometers per second. And since we know the distance the wave travels, we can use this speed to figure out how long it takes the wave to travel to each station. Remember that speed is the distance divided by time, so time will be the distance divided by the velocity. Record this time and the travel time in seconds on your Google Sheet. Now the time on our record section is in minutes, but we just calculated the time in seconds. So all we have to do here is divide the time we just calculated by 60. Then record this time and the travel time in minutes on your Google Sheet. All right, so we have a really big list of numbers here, and that doesn't do us much good because just reading numbers in a line isn't very helpful. It doesn't let us visualize our data very well. So we're going to make a graph. So on your Google Sheet, click on Insert and then Chart. You should get something like this that pops up. So we're looking to compare the geocentric angle of the seismic station to the travel time of the seismic wave. On our chart then, we want to reflect that. So let's start by changing the type of chart to a scatter chart. Now we have a bunch of dots and 3 lines. We only want 1 line. So let's start with the x-axis. Click on the 3 vertical dots and choose It. A box will pop up showing that right now the x-axis is plotted with column A. We want it to be column B. So change the A's in the What Data box to B's and click OK. If OK is not an option, the chances are good that you have a space before the first B. Go delete that and then click OK. In the series option, there are 3 lines. We only want 1. We actually only want the time travel in minutes. So delete the station location and the distance seismic waves travel by clicking on the 3 dots and choosing Remove. Then edit the time travel so that it is plotting the time in minutes from column F instead of the time in seconds from column E. That should give us a nice little graph that shows the time it takes for the seismic waves to travel to each station from the epicenter of the earthquake. Now take a moment and think about why this graph is not linear. The seismic waves travel at a constant velocity through our solid Earth. Why do they appear to slow down? Or do they? Think about the shape of the Earth and how that might relate back to how long it takes waves to get from one side of the Earth to the other. Now remember, we are testing a hypothesis. We just determined the time it would take for a seismic wave to reach certain points if the Earth were solid rock. To test this, we want to compare these calculations to the actual arrival times recorded by seismic stations in our record section. This is pretty simple since the record section has time along the y-axis. Take a ruler and line it up with the beginning of the P wave of each station and read across to the time. Record this in the actual time travel column of the seismologist part of your sheet. Now make a new chart with the station location on the x-axis and time travel in the minutes on the y-axis. So now we want to summarize our data. You have a Google document that has been shared in Classroom with you. You need to write a complete summary, including the 2 graphs and your Earth model and what the data means. So this is a pretty big one. This is about 10 sentences. So 1 sentence for each one of the bullet points on this page.